image in a different coordinate system, then you get a different image, of course, but the resolution does not change, and this is super important. So it's always this angular resolution and this range resolution. Okay, is that clear so far? Good. So, in real systems, it is just not true that you can do these approximations. And this is fun because many colleagues still think that radar processing is based on this approximation. And I heard many colleagues saying that radar is a narrow bandwidth thing or a small aperture thing. This is just not true. We work with systems with very large bandwidth and very large aperture. So let's say that this writing is a very strong simplification, but it just helps you understand how this image formation is done. In truth, this is the data we have to deal with. And how do you treat it? Well, it is not so easy because you see that the problem is not separable. It is not separable. Why? Because you cannot just operate column by column to focus the target onto different angles, because this shape is not separable. Now, how do you treat this data? Well, there are many approaches. Let's say those are just names, like chirp scale, omega k, fast factorized back projection, filter time domain back projection. We will see something about this processing algorithm, but not today, because what is very important to keep in mind is that the spatial resolution and the imaging properties will not change. So let's say I'm very sorry. My apologies. Okay, let me mute it. So. Okay, so what is very important is that the imaging properties will not change. So at this point, you should be able to focus a signal, let's say, to focus an image if the signal has been acquired under this simplifying assumption. You are not able to do the processing for a real system, but you are able to understand the imaging properties of a real system, because these equations will apply anyhow. Okay, so you can predict what are the imaging capabilities of a real system. And in particular, yes, maybe I want to show this one too. This is just the mathematical expression of what we have taught so far. So this is your signal after focusing, assuming a single target, of course. This is what is called the pulse response of your system. So you assume a single target, and so you have a single signal. This is the raw data, so before the pulse compression. This is after you do range compression, and so this signal becomes a cardinal sign. this is when you focus the signal, so you do your Fourier transform in time and frequency. This is the same if you express it in range and angle. And this is again the same if you express it in x and y. So I just let you think about this expression. I think it is very useful to be able to write the signal this way, but I don't insist on this now. Because what I want to talk about now is synthetic aperture radars. So, synthetic aperture radars are radars that employ a moving radar sensor, which is flown like on board an aircraft, a satellite, a car, a motorbike, whatever you like, in order to synthesize a very long antenna. So, what is the trick? We say that your angular resolution depends on how long is your array, right? So I want a very fine angular resolution. What I have to do? I need a very, very long array, which might cost a lot, because I need to buy a lot of antennas. So the idea of synthetic aperture radar is to just buy a single antenna, but move it along some trajectory. And usually this is done by satellite or aircraft. And so basically, in this way, we can form, if you like, a virtual antenna or a synthetic antenna, as it is called, which is anyhow the exact equivalent of the array aperture that we have just discussed. The spacing of the sensors along the array depends on the frequency with which you emit pulses. We talked about this PRI. You remember that pulse repetition frequencies. Sorry, the pulse repetition interval. And so let's say that you are moving. As you move, you transmit, receive, and so your delta x is given by the pulse repetition interval times the speed of your platform. One thing that I should have told you is that we will assume the so-called start-stop approximation, as in the exercise we saw about the rotating antenna, which means that we are assuming that the airplane stands still, transmits, receives, then makes a step ahead, transmits, receives, and so on. This is not really physical, of course, but since EM waves travel so fast as compared to the aircraft, this is an acceptable approximation. You can relax it, you can do it, but it is really not. Let's say it is a second order aspect. Now, the real question, talking about synthetic aperture radar system, is how long is the synthetic aperture? Because based on this picture, it should be as long as the full trajectory. So if I fly for 100 kilometers, then I should have an aperture which is 100 kilometers, which is really not the case. And why? Because you know that real antennas only emit on a certain sector. So, and we saw that this the angular sector where you are actually emitting power is more or less given by the ratio between the wavelength and the physical length of the antenna.
and of course also in the other direction you have this illumination. So just to give you some numbers, if you assume a spacebound system at C-band, so a short wavelength, then this delta psi, this angular sector, is on the order of half a degree. If you assume a clear-band system, so where the antenna has to be much smaller, of course, especially at longer wavelength, then you can have an angular sector of some 20 or even 30 or 40 degrees. So let's say that how the width of your illumination depends a lot on the system. So the key to understand synthetic aperture radar is to see that the targets are only illuminated for a fraction of the time. So when I am emitting here, since this angular sector is limited, then the target is just not responding. The target will only respond here, 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 and then it stops. Okay. So at the end, how long is the synthetic aperture? Well, it is the length depends on the target. So it is the length for which the target is actually responding. So if you consider a target at a certain distance from the trajectory, then the synthetic aperture is just given by this delta psi, which is again given by the wavelength and the physical length of your antenna, and the distance. So for a synthetic aperture radar system, the aperture length depends on the distance of the target. So short aperture for close targets, long aperture for far away targets. Now, if you have an antenna this long, then you have a capability to resolve different angles, which is given by this expression. This, maybe the slides are not very clear here. We say that this pulse width is 1 divided by A, right? We say that the special frequency fx is two over the wavelength time the angle. I am simplifying, so instead of the sine, I just take the angle, and this is true when the angle is close to 0. And so this delta fx, and this is 1 divided by A, this is equal to 2 over the wavelength times your angular resolution. And so your angular resolution is given by half the wavelength divided by the synthetic aperture. As simple as that. Again, take care. We say that this antenna, so we say that the synthetic aperture depends on the range, so your angular resolution depends on the range. The part of the target defined is your angular resolution, which means that you can So your linear resolution is given by this expression. Oops. And if you put all of these equations together, then you end up with this equation, which says that your linear resolution, so your capability to resolve different targets at different positions here, so different along track positions, is just given by half the physical length of your antenna. Right? And this is called the SAR paradox. So with real antennas, the longer the antennas, the finer the resolution, right? With the SAR, no, it is the other way around. The shorter your physical antenna, the finer is your resolution. So if you want to build a SAR system with a very fine resolution, buy a very short antenna. And so this is just to summarize some difference between array imaging, let's say antenna, array, and SAR. So for a SAR, you have a synthetic aperture which is sliding along your trajectory. You get angular resolution because you are forming a synthetic array in this direction, whose length depends on the distance, and so you have the same horizontal resolution for antenna. Concerning the antenna array, the big difference is that the length is fixed, which means that you have the same angular resolution for the target. One thing that I should have mentioned is that no, I will mention it at the next meeting. So this is an example of focused data for an array, and this is an example of focused data for a SAR system. Just notice that for an antenna array, what is constant is your angular resolution. For a SAR system, what is constant is your resolution along x. So the spatial resolution along the direction of flight. So, talking now about the SAR resolution cell. We say that, wait a sec, we say that geometrically, so we started from this point of view. Okay, if I just stick to geometry, our conclusion is that after a SAR experiment, what I can do is to locate a target on this signal. Okay. Then we have discussed the direction of arrival, range resolution, and SAR imaging. So you know that you cannot just so that, let's say, what you can do is to put a target on a certain resolution cell, and so your target will belong to this shape here. How do you say? So this looks like a bicycle tire. No? So at the end of your site experiment, what you know is that your target will belong to this bicycle tire, whose size is given by your along track resolution in this direction and your range resolution in this other direction. Okay. So, for example, if you take a look at the SAR image, then this means that each pixel is associated, of course, with a certain range and azimuth resolution cell. I forgot to tell you that the along track direction is normally called azimuth. So I will just confuse the term azimuth with the x coordinate. And so this means that the signal, the amplitude that you read in every pixel of the SAR image is nothing less than the result of everything into this bicycle tire, which is given if you look at this projection in this space, and in the elevation plane, it is everything that falls here at the same range. So, for example, here the blue pixel corresponds to the signal from the car, and the green pixels here corresponds to the signal from all the different streets. So, let's say that in this pixel, assuming that there is just a car, you are sensitive to the radar cross-section of the car. This other pixel, you are sensitive to the interference of all the trees together. And so this is more or less it. This is more or less it. I have about 20 or 30 more slides, but I have the feeling that I'm going too fast. So any questions? No?
I didn't understand why we have delta R. R is what? I lost myself 1 second.
Delta R is your range resolution.
Uh-huh.
So delta R is half the speed of light divided by the bandwidth. So is this clear?
How I can find the minimum R range for compute the resolution, algorithm resolution indexes?
The resolution along track.
Yes, the delta V.
Okay. Well, actually, you don't need to because.
Yes, in that case.
Okay. Right. So this R min is represents the minimum distance of a target from the trajectory. This is always the distance in the orthogonal plane. Just this is independent on the elevation of the target. You see, where is that? Here. So this R is the minimum distance. All the targets in this bicycle tire are at the same minimum distance from your trajectory.
But the minimum distance respect to the car, the mountain of a car is different. No?
Yes, but this is the trick. This is the trick. Let's say all the targets in a certain pixel here. So you form an image, right? And so you have many pixels. Let's say that you take this one pixel. Now, the value of this pixel depends on the target and in this azimuth position and at the same minimum distance from the radar. And physically, all the targets here are at the same minimum distance from the radar. So this pixel is the result of whatever falls into this resolution cell. And this is the concept of resolution cell. This, by the way, it might look as an ambiguity, you know, because you say, for example, in this case, you see you have many trees at different positions, but at the same distance from the radar. So they are just compressed onto the same pixel. But assume that you can look through the things. Then also an optical image would have the same ambiguity, because when you take a photo, what you get is that for every pixel the total power that is emitted from a certain direction, right? So if you were able to get the signal from different objects at the same angle, but at different on different planes, then you would just get a superposition of all these targets. So the world is 3D. When you take an image, you are just giving up something. So I hope this answers. Okay, so if everything is clear, we can just jump to commenting some XR images. So the first thing to be aware of is what is called speckle. Speckle is nothing else than interference among all the targets. I think that you saw speckle already with Professor Monti Guarnieri, right? Did you? Okay, well, speckle means that, wait a second, this is speckle. We say that you have here the signal from different targets. They are in the same resolution cell, whose size is the delta R, but they are at slightly different distances from the radar. And so they add up with different phases, which forms constructive and destructive interference, which gives you a random signal, more or less. And this is what is called speckle. This is a SAR image, or I would say that this is a grass field. And so you see, you do not see this as a uniform scenario, but you see all these black and white dots. And so this means that for each pixel you are getting a high or low intensity, because every single target in each resolution cell is adding up with a different phase. This is something that we did see, no? With me. When we talk about interferences, when we talk about resolution, we say that if two targets go into the same resolution cell, then they can cancel out each other. I'm sure we did it. Okay, this is exactly the same. So we can characterize this as in a probabilistic way and say, since the pixel is contributed by many targets with different phases, then I can characterize my pixel as a complex Gaussian variable with zero mean, because in average, there is constructive and destructive interference with a certain variance. This certain variance is this is connected to the radar cross-section of each single target in the resolution cell, and this is the variance of the square pixels, and this is a known property of the Gaussian variable. So the variance is given by the fourth power of the dispersion. I will go back on this, so do not lose too much time. But I just want to show you this. So this is a tropical forest. So again, vegetation, and you see here that these images, you do not have much contrast because each pixel is determined by this interference. How do you reduce this interference? Well, the most simple thing to do is to just take the absolute value of the pixel and do a local average. And in this way, you see, since you can look at the pixel in terms of a random variable, then by local average, you can decrease this phenomenon. Another very nice example is this one. This is an optical image of the Linate airport. So you see this very clearly. This is a radar image, which is not as good. There you see here, you have a lot of speckle. How do you reduce this speckle? Well, in this case, this was reduced by averaging the absolute value of multiple star images. And so you see that in this case, you are how to say, you are preventing these random variations, and what you end up with is a much more stable image. Now, there is much to say here.
Sorry?
Just a moment, yes.
I don't get the previous case. What's the point of taking local averaging? And I don't get how it works actually.
Okay. So, I'll try to explain this quick now, but this will actually be a topic for Thursday. Okay. So, the point is that you have this interference phenomenon. Okay. And this phenomenon will be different for every pixel. So, for every pixel, you can have either destructive or constructive interference. So at the end, you can fairly say that this is random. right?
So maybe if the average is null, we can take the average and then the
If you,
averaging it takes the interference to 0. Is the point?
if you take the average, then you get 0,
Okay.
and 0 is not a signal, or let's say
Okay, so-
it is not information. What you do? So what you do is that you characterize your signal as a complex, because it is complex, Gaussian, because by the central limit theorem it has to be Gaussian, zero mean, because you can have either constructive or destructive interference, with some variance sigma squared, which will depend on the radar cross-section, on the radar equation, so on your antenna gain. Here is the radar equation, right? Now, you would like a grass field to appear uniform, right? If you take a look at the grass field, you just see green. You don't see speckle with your eyes. With your radar, you see speckle. So, how do you prevent this from happening? Well, taking the average would not make much of a sense, because you would get 0. But you know that the expected value of the square of your pixel is sigma squared, which is connected to the radar cross-section of your target. So if you could get the expected value, then you would have a stable signal, right? Okay. Now, what do you do when you cannot take expectations, but you only have sample data? You do a sample average. So the key is that either to do a sample average in space, so you take multiple pixels and you just average, or a sample average in time, so you have different realizations of the same interference phenomenon, and you just try to get a stable result by a temporal average. Okay, so this is the thing. I will be back on Thursday concerning this topic. So do not spend too much time. I just want to show you some nice image. So this is the Vesuvius. Oh, wait. Before we do that, remember what we said about. Remember what we said about range. So your range resolution. So this means that if you are illuminated from here, imagine that you have a building, then how will this building appear in your SAR image? Well, this is the closest point. So this is the point which will appear first. And then you have all these other points. So in the SAR image, this means that this building will appear upside down, because first you have the roof, and then you have the base, right? For the same reason, if you have a mountain, then you will have that, for example, these 2 points on the same facade, on the same side of the mountain, are at the same range. And so all these points can be just squeezed onto a single pixel. Whereas on the other side, then you have an almost, let's say, on the other side, you have that all the different points will appear in different range. I just showed you some images. Okay. First, this is the Vesuvio. Huh? This is an image of the volcano Vesuvio as imaged by the European Space Agency satellite ENVISAT at C-band. So this is the upper caldera. This image is not very good because the projector is not very good, but it really looks nice on my screen. So you can see, for example, that this side is much longer than this other side. You see that it appears to be tilted this way, and this is exactly this phenomenon here. So you can for sure say that the radar was flying here and was imaging the mountain from this direction, because you see that this side is much shorter than this other side here. It's even more clear if you take these, if you see these images from Barcelona. So this is the Torre Akbar. The base is here, so the tower is physically here, but you see that it appears this way in this image. So a question for you: where is the system flying? Or which is range and which is azimuth? So just take a look at this picture. The top of the building is the closest point to the radar, right? And so the radar has to fly this way, or let's say the flight trajectory is here, because this is the closest point. So first comes the top and then the bottom, and this is the facade of the building. So you see in this case that this building appears upside down. I think I have other nice images. Okay, so this is in Milan. This is a Google image, and this is a X-band image by Cosmos Skymet. Again, it's much better on my screen, not so good here. And this is a stadium. Is this Barcelona? Okay. So again, you see how the stadium is tilted according to the same phenomenon. So I think this is it. So I tell you, wait, before you go, just one thing. I see that with the slides I go a bit too fast, or it seems like that you cannot ask the right questions. So I wasn't expecting to do all the slides today. I think that the last part was not very clear. So, am I right? Okay, you're right. So it's my fault, it's not your fault. What we shall do on Thursday will be to write a simulation doing this. Okay, I will try to change perspective. So I will not come with a simulation which is done and we just comment on it. But I want to write a simulation here with you. Okay, so bring your laptop if you like. It is not compulsory, but it might help. It might help. So bring your laptop on Thursday. We will just write a simulation from scratch. Okay.